We're going to continue now with our work of different ideal gas processes, expansions and compressions and heatings and coolings, using the ideal gas law again, but now we're going to look specifically at what we call PV diagrams. So we use these a lot with gases. It's just a diagram with pressure on the y-axis and volume on the x-axis. And so we'll keep referring back to the ideal gas law, PV equals nRT, and for all of these we're going to treat N and R as constant values. Now R is always a constant, it's the universal gas constant, so that never changes, but N, the amount of gas, that could potentially change. We're just not going to consider those cases at this point in time. So for each one of the special cases that we looked at in the previous videos, now we're going to identify or sketch out some graphs of the PV, or sketch out the PV graphs or PV diagrams for those situations. So isothermal expansion or compression. First off, we know that we're going to have some changes in volume because we have expansion or compression. That means taking up more space or taking up less space. We need to identify what else is going on in this this situation, though. So isothermal means constant temperature, a constant T. So in this case, PV is equal to nRT. All three of these are constant values. So I could write that as PV equals some constant. Or if I rearrange for P, which is on the y-axis, then P is equal to some constant number divided by the volume. So this is an inverse graph. So PV diagrams will look like inverse graphs, like 1 over x style graphs. So we have kind of a general shape like this, and depending on the conditions of the gas, you might have a number of different positions, but it's always going to be a 1 over x shaped graph. So this constant will determine where that line is. Now these lines for isothermal expansions or compressions, we call these lines isotherms. Each one of these lines is an isotherm, and so we'll refer back to those later on when we talk about adiabatic expansion or compression. So keep those in mind as we continue. But if we see on this diagram an inverse curve like this, a 1 over x style curve like this, we know that that's an isothermal expansion or compression, a process where pressure and volume change, but temperature is remaining constant. Isochoric is a process where volume does not change. So PV equals nRT. Isochoric is kind of a specialized term for this. You might just see this described as a constant volume heating or cooling, or an isovolumetric heating or cooling, are other terms that people use with these. So here the volume is constant, and N and R are constant. So if we rearrange this, P is equal to nR over V times T, where this is just some constant, so pressure and temperature are directly related. Temperature isn't shown on this graph, though. So in isochoric heating and cooling, as we change the temperature, the pressure will change, but volume will not change. So we show that as a vertical line. Pressure changes, volume doesn't. So depending on what our starting volume is, we might have any of these different lines here. In the previous example, these isothermal lines, those get called isotherms. I've heard these called isocores before, but again, I don't think that's a real common term, so you don't need to worry about it if you aren't familiar with that. Now it's useful to note that since work done on a gas is equal to the pressure times the change in volume. We have to have a change in volume in order to be doing work on a gas. In each one of these processes, we have no change in volume. So each one of these, we know that no work is being done on the gas, and the gas isn't doing any work on its surroundings. For isobaric expansion or compression, pressure is held constant. So PV equals nRT. So pressure and N and R, those are all held constant. You can rearrange this as volume is equal to nR over P times T, where this is just some constant value. So we see again that there's a direct relationship between volume and temperature, but temperature doesn't show up on this graph. So all we really need to know here is that volume changes, but pressure does not. So that's going to be a horizontal line. And the starting value for that pressure will determine where that horizontal line is. These lines sometimes are called isobars. Again, not a super common term, so you probably don't need to worry about that too much. And then with adiabatic expansion or compression, this is the one where we have no net transfer of heat in our system, but pressure and volume and temperature, those can all change, and they all do change in adiabatic expansions or compressions. So in these ones in the previous video, one thing that I mentioned here was that basically pressure changes more, so pressure change has a bigger change as a result of a specified volume change than it would in isothermal expansion or compression, because that temperature now is going to change. It's not held constant. So as our volume decreases, as we get closer to the y-axis here, a decrease in volume causes an increase in temperature, and that increase in temperature adds to this increase in pressure that we experience. So the particles not only are impacting the sides more often because the container is smaller when volume is smaller, they're also moving faster when this temperature increases. So they're moving faster, they're hitting the walls of the container harder and more frequently as a result of that. So if we look back at the isotherms, this 1 over x format, looks something like that. These are isotherms. Our adiabatic expansion or compressions, those are going to cross over these isobars because pressure changes more rapidly. So we'll have a steeper line here and then a more flat line, a more rapid change to a flatter line here. So we might see something like this, where we're crossing isobars. Now, one thing that's worth noting here is that each one of these adiabatic expansion graphs will cross over each isotherm exactly once. So maybe I should be a little more careful in drawing this one. It doesn't expand or doesn't change pressure quite as rapidly as I had originally shown, because that would have it crossing that isobar. Oh, no, I guess that was okay. It was a different isobar. Anyway, so these red lines, the adiabatic expansion graphs, they just tend to be more extreme. They get vertical really much more rapidly when they get close to the p-axis, and they get almost horizontal much more rapidly when they get close to the v-axis.